Hill. I'm Carlton Perkins.
I'm Sean Tubau.
I'm Tyler Thomas.
I'm Raymond Wilshire.
I'm Thomas Magnini.
And I'm Kevin Coles, and we're working on the microgravity scale.
Over the past 3 years, we have designed and constructed a device that will give astronauts the ability to measure the mass of objects in a microgravity environment.
Our device applies centrifugal force to two objects, a constant mass and a variable mass. We use a DC motor geared to a center column to accomplish this task. This center column contains two force sensors mounted to either side of it. This data is then compiled to calculate the mass of the variable. Additionally, we have incorporated an optical encoder to regulate the speed of the center shaft to yield more precise results.
I'm Amy O'Brien.
I'm Connor Schultz.
I'm Ethan Mullen.
And I'm Mike Sarrazin.
And we're working on a system that will reduce the radiation exposure astronauts face on the ISS daily. For our systems, we came up with two solutions. Our first solution was a blanket, and our second solution was a module. For our blanket, we used sodium polyacrylate to gel the water. And once we gelled the water, we put it into a containment so it wouldn't leak. And the sodium polyacrylate brought down the radiation counts by nearly 94% when we tested with our Geiger counter and radiation source. And then we also used a very flexible lead as our other layer because it brought down radiation by nearly 92%. And finally, we covered it, both of our materials, with our Gore-Tex because the Gore-Tex is an ISS approved material.
The second aspect of our project is a radiation module for the station. Our design has incorporated ideas from the Orion spacecraft for a manned mission to Mars. Their design incorporated water and lead in the walls of the spacecraft to further protect against radiation. Our module was designed in a 3D CAD software, the dimensions of which are similar to that of the Leonardo module already located on the station. We incorporated lead, water, and graphite in the design. This is to help further protect against radiation on the ISS.
I'm Tyler Clementi.
I'm Torin Ameling.
And I'm Zachary Keeler.
The problem that we were trying to solve is to design a process of molding and casting 3D parts in a microgravity environment.
And our solution is using thermoset polymers and centrifugal force to shape mold material around 3D printed parts.
We designed this part to allow us to test the strength of casting material.
Here we are assembling pieces used to create the mold.
Here we are mixing molding material through a static mixer, also injecting into the test tube.
Next we are inserting the test tube into a centrifuge which provides centrifugal force to eliminate bubbles and shape material.
Here we are disassembling the tube, extracting the fully cured mold.
Next step is to cut the mold into two pieces using an X-Acto knife, also removing the molded part.
With the model part removed, we place the two halves back into the tube for casting.
Using a smaller static mixer, we inject urethane plastic into the mold.
Next, we place the test tube back into the centrifuge for a lower RPM and shorter time.
Lastly, we disassemble all the parts of the tube and remove the casted part from the mold.
My name's Andrea Renovato.
My name's TJ Bourget.
My name's Adriana Oliveira.
My name's George Wood.
Our application's primary goal was to help astronauts deal with desynchronisis caused by a chaotic training schedule while preparing for life in space. While on the ground, astronauts must travel extensively throughout multiple time zones, which can cause astronauts' internal clocks to become oriented. The long hours may also cause astronauts to be constantly tired and suffer from lack of sleep. This app solves these problems by properly scheduling sleeping periods and managing appointments while adjusting for the many time zones that astronauts may utilize.
I'm Cole Bechet. I'm working on exercise concepts. The goal was to reduce anemia, bone density, or muscle loss aboard the ISS. So to help that, I've designed a suit that will enable them to exercise their muscles better by incorporating these high resistance elastic bands. So as they're moving about, they have to use a lot of resistance to move their muscles, and basically that would reduce the amount of muscle loss. What I did is the muscle groups I was going to exercise is the legs and arms. Those are the most important they need to use, so when they come back to earth, they're going to be less affected by the gravity.
Hi, I'm Rich Hepburn.
I'm Gavin Proseed.
I'm Max Williams.
I'm Andrew Urquhart.
I'm Joe Caritas.
I'm Ryan Kester.
And we're doing the anti-vibration box.
Our HUNCH project is the anti-vibration box. It protects sensitive materials and equipment from the highs and lows of vibrations during takeoff and landing. Our system is made out of 80-20 aluminum, high-strength elastic bands, turnbuckles, 3D printed parts, and milled aluminum parts. During testing, we have gathered that our system has an 85% vibration reduction rate from the outside of the box to the inside of the suspended box. It's a tunable system. By twisting these turnbuckles, you can make the system more rigid or relaxed depending on the environment and the vibrations. It can be packed into the mid-deck locker at any orientation, and it can be moved around without the cargo slipping out. The cargo is rigidly fixed to the bottom of the inside of the center box.